we're talking about ancient solutions to the heat equation, and we're still in the midst of proving the first result, which is a representation formula in terms of some measures, a non-negative Borel measure and just a Borel measure. And what we've done so far, just to recap, let's just recap this really quickly. Okay, so, all right, this is just Liao. We've taken, now I don't know, I've got a zoom thing in the way here, so I'm gonna move it over there. That just means my head will, I don't know, change its orientation, it'll reverse its orientation. So we use Liao to show that the time derivative of an ancient non-negative solution has a sign. And then because the time derivative is a solution again, you get the same thing for all time derivatives. And then by changing the time variable from t to minus t, you obtain that that mapping is a completely monotone function in the sense of Bernstein. All right, so that's that one. And then Bernstein gives this integral representation in terms of the non-negative Borel measure nu, which is this part here. Okay, and then by just doing some manipulations of this integral, we were able to write fxt in terms of, maybe I'll just minimize this somehow. Okay, whatever. We're able to write this, okay, this fxt as an integral of t e to the minus st times a function h, which is the integral of this Borel measure. And now, what I said last time, this is basically caught us all the way up to last time, that this was something like a Laplace transform, and you can see that because this t here is independent. You can take it out the front, and so once you take that t out the front of the integral, you can really see that this is like a Laplace transform. So, okay. So let me go to the next page, inverse Laplace. So I think, is that too thick? No, it's all right. So what we've got here is integral of e to the minus ts. It does look a bit too thick, but I don't know how to change it. I don't know why it's thicker for some reason. I've got the same things pressed anyway, whatever. Maybe it's zoomed in a little bit or something. And they have this function h, oops, not t, x, s, and then this is ds. This is 1 over t, right? So we've divided by t, and then we get u of x and minus t. And now it's also a result of Bernstein that this representation extends into the right complex plane. So for t positive as an entire function, and just from estimates for the heat equation, you obtain uniform estimates on any compact subset of positive time multiplied by Euclidean space. And so then you can take an inverse Laplace transform and you get that h of x and t is 1 over 2 pi I, and this is just the inverse Laplace transform integral, right? Because now the s variable is complex. Okay, and then you've just got this thing. Oops, not t, did it again. S, S, ds. Okay, that's that step. Okay. All right, now let's go for step 5. This is called integral estimate. One of my favorite things to do, at least, integral estimates. And now let's just note or recall, I guess, if we forgot, that the Laplacian of this f function. Now this f function is just the name that I gave the map that reverses time. So it's a solution of the backward heat equation. Is 0, and that's in Rn cross 0 infinity. So what this means is we can test this equation with a smooth cutoff function and integrate and basically just have some fun playing around with some integrals, which is pretty much my entire mathematical career, playing around with integrals. Okay, so what do we get? We get ddt, so we're going to test this with a phi, right? This is Euclidean, so there's no worries about measures evolving or anything like that. Well, there is a measure that evolves actually, but it's not dx. Okay, so we have this, and that's minus the integral Rn, and then you take phi x, and this is Laplace f x t dx, and all right. And of course, my favorite thing in the world to do, integration by parts. I want to move this Laplacian over to phi, and of course I can because it has compact support, and it's smooth and wonderful. So that's what I do. Okay. Now, what we're going to do is use our expression for this function here, this fxt. So we've already calculated back up here, not there, here. We have this expression for fxt in terms of integral t e to the minus ts h of x and s, and we have this formula for h, which is the integral of d nu, and so we're going to put all those things together, sub them in here, and we're going to get, oops, I'm still red. How do I, here we go. And we're going to get minus integral Rn, and so we have to pick up another integral here, and we're going to have s e to the minus ts. Okay, phi of x, and this is d nu x and s. Okay. All right. And so what that means, okay, so that means these two things are equal, and we get a, okay, let's just write it down. Try not to go too fast. Okay. Okay, so this is equal to the integral over Rn, and this is the integral from 0 to infinity, and we've got e to the minus ts, and then this is Laplace phi x d nu. All right, but that's great, right? Because that basically, well, not basically, that's again a Laplace transform of something, right? So this is the integral 0 to infinity, e to the minus ts, and then you've got the integral over Rn, Laplace phi minus s. So you see this operator Laplace minus s, which is somehow playing the role of the Laplacian for, so Laplace minus s plays the role of Laplacian, but for ancient solutions for the heat equation, at least on Rn. Okay, now this is 0. This is for all t bigger 0 and phi smooth cutoff functions. Okay, that's our integral estimate. Alrighty. Oh, that's the end of the page. Okay, so step 7. This is, we're going to derive a PDE for this function h that's going to be true at each t.
Step 6, I think.
Oh, is it step 6? Thank you, Paul. You can fix the numbering later. I'm not good at arithmetic. It's quite difficult, especially counting. Counting is very hard for me. So, all right, so we're going to try to be very careful because I'm not great at, well, I'm not great at much, but I'm not great at measure theory, that's for sure. So we're going to take it slow. Define a signed measure, e to phi, okay? It's going to be a measure on 0 infinity, and it's going to be the integrand, right? It's the thing that we take the Laplace transform of. D to phi is going to be, okay, this integral that I just wrote up a second ago. Like that. Okay, and then what we've shown is that the Laplace transform, well, however you want to write it, I'll just write LT, but it is exactly the thing that I wrote down a second ago, is 0, and then that implies, of course, that the measure is 0 as a measure. And now, what does this really mean? It means that when we take this measure and I'm going to use the word measure a lot today, and we measure with the measure at the interval, then we get 0. That's what it means. Okay, but this thing also has a definition, of course, and we can pass these integrals through, and we get this. Okay, this is an S. And then, okay, so of course, this thing here is our old friend, H, X, and T, right? And then I haven't finished this equation. My handwriting is too big for some reason. This is a bracket here. Oh, Glenn. This is a bracket here. And then we've got minus phi of X, integral 0 to T. And then this is S. Go away, emails. I don't know if you guys can hear that. Hopefully not. S d nu of X and S. All right, sweet. Okay. Now, what we can do, what we love to do, is integration by parts, or at least I love to do integration by parts. One of my favorite things to do. And because you see here in this integrand, all right, let's just make a little side area like this. In this integrand, integral, we've got integral 0t of S d nu xs, right? But because h of x and t, or you could replace the t with a different variable, maybe it's more obvious, x and say u is integral from 0 to u d nu x and s, then you can integrate by parts because the d nu here is just the derivative of h, right, with respect to u. And so you can integrate by parts. And the good thing about it is that when you do that, you pick up a boundary term, just one boundary term because the other one is 0 because of the 0 here. And then you differentiate the s. And so then you just pick up h again, right? So it's a nice little, I don't know, undergraduate math trick, which we love to do. Okay. So basically, okay, so maybe I'll just scroll down a bit because what I want to do is put these integrals. Okay, so So I'm going to move this integral over here, and we're going to see that integral Rn, Laplace phi x, integral 0t d nu xs. Okay, that's that integral there. I don't need the dx. That's equal to integral Rn phi x integral 0t s d nu xs. And okay, and now we do this integration by parts, and that I was talking about. And something cool is going to happen. We're going to get phi x, and then the boundary term is t, h, x and t, and then the remaining term, okay, just when you do that substitution that I mentioned a second ago, is also integral of h. Now I do need the ds, and I need the dx. Okay. All right, so what does this mean? Let's take a look. So this again is another dE, right? And this is a dE for h. Okay, because this is true for any phi in CC and phi, we have a dE for h for at each t solves. Now, what's it going to be? Because this is h here on the left, we're going to have Laplace h, x and t, and on the right, you're going to have t, h, x and t, and then this integral minus integral 0t, h, x and s, ds, like that. Okay, so then of course, h is smooth as a solution to that dE. Okay, anyway, that's not the end of the story, but you can see again, you've got this operator, right? You've got this Laplace minus t operator applied to h. Okay, and we've got this other little awkward term, which is what it is. Okay, anyway, it's not that bad. Okay, so that's our dE for h. I think I'm getting close to the end of this page. Yeah, so let's make a new page. Okay, so now the next step, Paul, correct me if I'm wrong, but maybe it's step 7, I hope. We're preparing for Harnack. Okay. All right. So basically what we want to do is we want to derive some, okay, so we're going to fix the x and take the measure nu now with a fixed x, and if you apply it to an interval, then this is our function h at x and b minus the function h at x and a. Okay. Okay, so what is this for I? Well, you don't need to write that. Let's write since. What we're going to do is we're going to turn our dE for h into estimates on the Laplacian of nu as a measure, and that will allow us to prove an estimate, which will then allow us to differentiate nu and do a change of variables that will finish the proof, basically. Okay, cool. All right, we have Laplace nu x. I just want to call this I. Like that. It's being lazy. Okay, so just looking at the DE here, let's just do this. Laplace H xb minus Laplace H xa. If we just look at the DE, then we're going to get, for this first one, we're going to get b h xb minus integral 0b h x s ds. And then for the second one, we get the same kind of thing, but with, different sign, and b swapped with a. That's a 0, sorry. H x s ds. Okay, and of course you can combine these things together, which we do straight away. And they have a very nice structure, which we're going to exploit in just a hot second. Okay, so this is minus integral AB H X S ds. And all right, cool. So we want to estimate this from above and below. All right. So the first thing we do is, okay, so we can add and subtract the integral of h of x and a from a to b, right? So, so b minus a times h at, this is again sort of scratch calculation, x and a. All right, this is not hard maths, but anyway, this is integral from a to b of x a ds, right? We're going to add and subtract that, okay, and then we're going to see if what we've got makes sense. Okay, so first the a h x a term is going to cancel, and you're going to have b times h x b minus h x a, and then here you're going to have minus integral a to b h xs minus h xa ds. Okay, now does that make sense? So minus minus makes a plus, so we added that, so we have to subtract it. The minus a cancels and then factorizes with the b, so I think it's okay. And now what, okay, so let's also recall that h is non-decreasing, right? Because it's the integral of a non-negative measure, so it can only increase. All right, and that means that in this, I might decrease the size of this. That means that inside here, right, you've got, oh, this a to a. Guys, what? A to b. All right, anyway. Okay, so h, x, and s is bigger than a, right? So this difference is going to be greater or equal 0. And so this whole, so when you put the minus out the front, you're going to get something less than or equal 0. And then this thing in the brackets here is nu x of I. Right? That's here, right? It's just off the screen. I was AB because I was too lazy to write AB all the time. All right, cool. Cool beans. So now go back to my thick pen. What do we want to say? Less than or equal to, I think we're doing. And so we keep this b floating around, which is just the supremum of I, so it's pretty nice, pretty nicely controlled. And then this is the measure of I, just like that. Okay, so let's, because this was a bit far away, let's do this. Nu x of I, which, you know, you can think of this as saying, well, definitely this. Okay, whatever. Now we can do the same thing from below. And I wonder if there's an easy way to look at this and just do it. So, okay, so let's, okay. Okay, from below, we're going to get, okay, so we start off at the same place, nu x, I. It's bh xb minus a h x a minus integral ab h x s ds, like that. And yeah, we get the same spot. But now instead of adding and subtracting the integral of xa, we add and subtract the integral of xb. Okay. And so what that means is that we're going to get the b terms cancelling, and instead we have a times h xb minus h xa, and then we've got minus the integral ab h xs minus h xb ds. Okay. So it's using exactly the same idea. There's nothing special has happened there at all. But now let's have a look to see where the signs line up. Again, h is non-decreasing, so h at x and b is going to be bigger than h at x and s. So this integrand here is going to be less than or equal to 0. And then with the minus sign, greater or equal to 0. And then, okay, and then inside here, you again have the normal, the measure nu x of I. Okay, cool beans. So then we get greater or equal a nu xi, which means that we have this kind of estimate. Okay, so all right, that's our preparation for the Harnack that we're going to use. So these two estimates together, I'm just going to give them the same label because I'm super lazy. What this means is that we have a two-sided estimate for this ratio. So in other words, if you make the ratio into a function, then that function is bounded. Okay, so let's do that. So how much space have I got down here? Not much. Let's make a new page. All right, so call it C because that's what people normally call this function when you write down a PDE. So you have this, satisfies, okay, it's bounded by whatever the max of well, let me just, it's bounded by B, I think. It's bounded by B. Okay, on Rn. All right, and then we go step 8. This is Harnack. And right on Nicodeme. Okay. All right, therefore, Harnack for the elliptic operator Laplace minus C implies, okay, so that basically lets us compare the value of the measure at x to the value of the measure at a fixed x, okay? If you think of the Harnack inequality as like a type of oscillation estimate, then this makes a lot of sense, at least intuitively for me. Okay, so nu x of I is bounded by a constant that depends on how far away x is from the origin. We're going to use the origin as the special point. You've got your estimate B for C, which we had up above, and then there's nu 0. Okay. And here, by the way, sorry, I forgot to say it, but I'll say it here. I is actually 0b. Sorry. Yeah, I changed my i's. Okay. That's it. Basically, what this is telling you, and what, you know, I'm sure you would teach your students in measure theory, is that this means that the measure nu x is absolutely continuous with respect to nu 0, right? So let me just write that. Is absolutely continuous with respect to nu 0. And then we apply Radon-Nikodym. To show that d nu x, d nu 0, okay, is bounded by this constant. This is just a direct consequence of the theorem. And here, of course, s is less than or equal to b. B was pretty arbitrary, though, so it's not such a big deal. But the constant depends on b. And the distance of x from the origin. All right. Okay, so now what this lets us do is conclude, okay, so now that we can differentiate nu at x with respect to nu at 0, we can do change of variables. And that's what this is all leading up to, an epic change of variables. All right, so I would like to call this step change of variables, but instead I'm just going to call it PDE for this derivative. Okay. And we're very close to being finished. Okay, so this thing is locally bounded as a measure. And all right, so let's do this. So we have integral 0 infinity e to the minus ts. This is from before, right? This is what we got from our integral estimate when we did, you know, we played with integration by parts all that time ago. Feels like an age ago. It's probably 20 minutes ago. Don't know how long ago it was. D nu, okay, x, s, like that. That's 0. All right, change a variable. We're going to get e to the minus ts, and then what we've got here is we're going to turn this into an integral on the outside with respect to d nu 0 of s. Okay, so what we've got to have in the middle is this Radon-Nikodym derivative. It's actually not that hard to remember. Yeah, of s, and then this is dx, and then this is d nu 0 s. Okay, cool. Now what this means is that nu 0 almost every s, this is the little past transform of signed measure. And okay, so let's do it like this. This is the past transform of oh yeah, no, I want it there, of this signed measure. So for nu 0 almost every s, we have, okay, what do we have? Oh, we're out of space. Well, I'm just going to write it at the bottom. Integral on Rn, guys, it's an n again. Plus phi x minus s phi x. Okay, now this is d nu x, d nu 0, s dx equals 0. Okay, great. Now this is actually for all phi in CC infinity on Rn. So of course this means that the measure, the Radon-Nikodym derivative satisfies this PDE, which is what we're going to say next. Okay, so that means that you take this Laplace minus S operator for each S, or for nu 0 almost every S, and you get d nu x, d nu 0, S plus 0. Cool. And of course, this is smooth as well. Yeah, so d nu x, d nu 0, S is smooth, and this d is satisfied. All right, cool beans. Brilliant. Well, this is a well-studied PDE. And in particular, we have a representation theorem for solutions of this PDE. And so, yeah, so I mentioned this before, but I didn't go into any detail, and I'm not going to go into any detail. But Caffarelli-Lippmann in 82, and if you are really interested in this stuff, then you should also check out Karapelovich, which is from 67, and Koranyi, which is from 79. Okay, these Caffarelli-Lippmann directly deal with this equation, whereas Karapelovich and Koranyi are looking in slightly different settings, but the ideas are very similar. Anyway, show that d nu x, d nu 0 at S is actually the integral over, and then our boundary is Sn minus 1, e to the x dot psi root S, and then you have this Borel measure d nu S, and then the variable is psi. Yeah, and so I'll just say that here for nu S, a Borel measure on Sn minus 1. Okay, and that finishes the proof, because you just follow back you just go back through the definitions. So we are done, because u at x and minus t was that fxt thing, which was the integral from 0 to infinity of e to the minus st d nu x, Glen, can't write an S, which is, all right, which I want to make I want to make t to minus t, otherwise the formula looks weird. Okay, so then you get u at x and t is the integral from 0 to infinity, integral Sn minus 1, est, right? I just did t to minus t. And then you've got to multiply by the other exponential. So you get x dot psi root S d nu S, that takes variable psi, and d nu 0 S, which is a non-negative Borel measure. That's it. Okay. So that's all well and good. If there are any questions, happy to answer them, but I'd like to do a bit more if I could today. But yeah, happy to answer any questions. I think we started a bit late, but that's my fault because of my son.
Glen?
Yes, Julie.
Just remind me what you're proving here.
This formula holds for general non-negative solutions to heat ancient solutions to the heat equation on Euclidean space, not assuming any kind of growth.
Right.
Yeah. Yeah, this formula. I'm trying to prove this formula. Yeah, did I write it down up top here? I'm not sure. Should have. Here it is, yeah, theorem. So use a non-negative solution to heat equation. It's ancient. And yeah, you get this family d mu. I guess I wrote of S here, which are just Borel measures on Sn minus 1 and non-negative Borel measures on rho in time. And yeah, you get this formula. That's what I'm trying to do. And so what I'd like to do now is just add a few remarks on the manifold setting. So I really thought I would be faster. Anyway, okay, so the manifold setting is slightly not problematic, but it's slightly, okay, let me just write things down. Okay, so we were in Rn, and we want to replace Rn with a manifold Mng. And the simplest thing that we could do, or at least the most straightforward one, is to assume it's complete, non-compact, non-negative Ricci, and then you get Li Yao working, which is great. And the same kind of argument works to show that you get this kind of representation for your solution, okay, where H is going to again solve the same PDE. Okay, so it's going to solve Laplace minus S H Sx equals 0, and here X is in M. All right, now the issue is, at least as far as I'm concerned, is that this PDE, the classification of solutions to this PDE is quite hard, and I don't fully appreciate it or understand it. But plenty of people have worked on it, and so what I'd like to do, if I have the, if I can do it in 5 minutes, is just summarize the statement basically of what happens on a Riemannian manifold, but not go through the details. And okay, so the key concept here is of something called a Martin boundary. Okay, now this was, so some things to look at. I'm not an expert, but Martin's papers in 1941 in Transactions, and Murata has a series of papers. The ones that are referenced by Lin and Zhang are the 86, 93, 02, and 07. If you just look at Lin and Zhang, you'll get those references. And okay, they don't directly apply to this setup, but what they do is they provide. So what we did in our proof is we used a lot of properties of, exponential function and so on. And what these papers do is they provide you this thing called a minimal, it's not minimal in the sense of zero mean curvature, but minimal positive solution. I'll write down in what sense exactly it's minimal, that pretty much plays the same role, but you have to replace Sn minus 1 by these Martin boundaries. And the structure of the Martin boundaries, and also the structure of this positive minimal solution, which is constructed via Green's function, is really difficult. So we don't have as such an explicit formula, but we still get a representation formula. So I'll write it down. Okay, so this stuff all together tells you that you have representation here. Okay, and the sigma is for the Martin boundary, and this script P is for the positive solution, minimal positive solution. And I'll write down what these things mean in a second. Okay, and here mu is a unique non-negative. This is just like before. Borel measure on sigma, and the measure of sigma take out sigma 0 is 0. Okay. All right. So what are all these objects? Let me have a crack at giving you an idea. Okay, so sigma 0 itself is the set. So it's the equivalence class of sequences of points on which, once you work out this Green's function, you get a minimal solution. Okay, so this is like this. Minimal. Okay, and then just to write it down, because I said it before, a solution is called minimal if, if you have any other solution. And by solution here, this S, you might be wondering what the S is. The S refers to the S in this operator. Okay, so this is Laplace minus S. This S is the S in that operator. Okay. Okay, so if this is true for some other function v, then v would have to be a constant multiple of the p. Okay. And then you might be asking, what is the p? Well, yeah, the p is that minimal thing that I was telling you about a second ago. It's defined via the Green's function. So you take the Green's function. The Green's function has an s in it because it's the Green's function for that operator, which has an s in it as a parameter. So you just divide the Green's function x and y with Green's function at some distinguished point, x0 and y. This is for y not equal to x0. Okay, and then it should be 0 if y is x0, but x is not equal to y, and otherwise it should be 1 if everything is equal. Okay. Right. So gamma s is the minimal Green's function for Laplace minus s. Okay, now I can state the thing. On a manifold, we've got this theorem. This is, of course, Lin and Zhang. Okay, it looks like this. Let Mg be a complete Riemannian manifold with non-negative Ricci. We take U as an non-negative solution, ancient to the heat equation. Okay, and then okay, so the completely monotone thing happens just like before. It's really quite direct from Li and Yao. Completely monotone in T, and then you can use Lin and Zhang's arguments to construct this little H function that satisfies that PDE that I wrote down. And then you combine that with the work of Murata and Martin to get this representation formula. I mean, as well as the argument of Lin and Zhang that carries over from the Euclidean case. Okay. So family of non-negative Borel measures. Mu on the Martin boundary these are sigma S for, okay, this is the Martin boundary for, because the Martin boundary is defined with respect to a differential operator. And so this should be interpreted as like one object, Martin boundary for this operator. Okay, and a Borel measure rho on 0 infinity, such that okay, what have we got here? U of x and t is going to be the integral from 0 to infinity, integral sigma s. You still have this exponential factor. The exponential factor just comes from the complete monotonicity, right? This is from Bernstein, so it's not affected by any of this Martin boundary business. That happens when you try to find representation formula for this PDE. Okay, so it looks like this. All right, anyway, that's the manifold version. I'm conscious of the time. I know people probably have to go. I had to go last week, so can't blame anyone. But yeah, and usually I know people ask the speaker questions, but I have a few questions. So I don't know if any of these things are known. Conditions on MG such that there's some kind of equivalence, right? Because in the Euclidean case, these sets here, this sigma S, they're all the same set, right? They're all Sn minus 1. So are there conditions on M and G such that sigma S1 is somehow equivalent? I don't know how, but somehow equivalent, maybe by some kind of the motion of a killing field or something, or a conformal killing field maybe, such that they're equivalent in some way, like some kind of control on how they change in S. Are there conditions that we can place such that we can determine the structure of sigma S? I don't know. I know that there's work of Rick Shane, I think, when the sectional curvatures are bounded between two numbers, but that was also for a slightly different problem. So anyway, I'm not sure. And yeah, what is PS? I don't know. It's not an exponential, I guess, but some sort of, I mean, yeah, I don't know. Is there a perturbative result? Is there some sort of way to pin down and to get more information out of this formula, which at the moment, at least to me, seems pretty opaque. Yeah, so I guess I should stop. I only have a little bit left, and the bit I've got left is quite special. I'll just give you guys a 30-second description. Back when we started talking about these ancient solutions, and before Ben gave even his first talk, or maybe around when he gave his first talk, maybe just after, he showed us an argument that lets you basically prove the dimension bound on ancient solutions with polynomial growth in a very, very quick way. It's very, very direct, very quick, and very simple. And so the last thing I'm going to do is we're going to prove, oh, and the kicker is that the order of the estimate is better than Lin and Zhang. The order is the same as the order that Colding and Minikotzi get in their papers. And so I want to, very last thing that I do, which I guess is going to be next week, is just to present to you guys Ben's beautiful argument that will prove Lin and Zhang's theorem on the exact sort of expansion of an ancient solution with polynomial growth in terms of a polynomial in T, where the coefficients are polyharmonic functions. And then from that expansion, you can work out fairly quickly the dimension estimate, because each of those functions, you know, you can work out using induction how many of them there can be based on the work that Ben presented on Lee's estimate, basically, for the dimension of the space of harmonic functions with polynomial growth. Okay, I'm very sorry I went over time, but yeah, I'm done. If there are any questions, go for it.
Thanks, Ben.
Excellent. I have a question.
Yeah, Kyung-soo, how are you
Yeah.
going?
Hi. In the harmonic function case, in the harmonic space of harmonic function and positive bounded harmonic function is related to some structural manifolds, like maybe the dimension of the positive bounded harmonic function is same to the number of manifolds under some condition. So I'm just curious whether the structure of sigma S or PS are related to such a geometry of manifold or not.
Yeah, I would love to know. This is like perfect question. I don't know. I think it must be. It must be, but I don't know. Ben, do you know?
Not really. I don't know any details now, but I think you're right that it would depend on the structure of infinity in some way. But yeah, no, I mean, so if you had asymptotically Euclidean or something like that, you could probably say something more about the structure of these things, I think.
Yeah.
But I don't know any good results.
Thank you.
Yeah, I don't know, but it's a great question. There has to be results out there, but I'm just too ignorant to know.
Good, yeah.
So I guess in the end, we're not going to use this representation formula for anything. But I think it's nice anyway. I mean, I like it how it does not require any growth condition.
Yeah.
That's nice, but yeah, you definitely don't need it to do it. Oh, there's a remark I forgot to make, which I don't think I'll write it down, but the remark is that you don't need non-negative Ricci. So you can get a Harnack inequality in a different way, and you can get away with not needing non-negative Ricci. So yeah, I didn't want to say too much about it, but at least for these kinds of lectures, I think it's definitely worth going with non-negative Ricci instead of just saying that, you know, there's a volume doubling and there's a mean value inequality and there's a Harnack inequality and so on.
So what do you need for Harnack? It's something like doubling and there is a Poincare inequality or something like that?
Yeah, I'm not sure. Poincare, I guess. Ricci curvature bounded from below, Poincare and volume doubling, maybe? Yeah.
Right.
I suppose. Yeah. Does that sound right? Who proved that?
A bit surprised if you need the lower Ricci bound and the other two. I mean, that would imply some of those parts. But anyway, yeah.
Yeah, I don't know. Maybe that's probably not optimal, but
yeah, people like I don't know, is it Selov-Costa and Sturm and so on looked at all these things, and I mean, at least morally, in a very general sense, parabolic Harnack's equivalent to volume doubling and Poincare.
Yeah.
Yeah, okay. So you don't need Ricci lower bound?
Well, no, I mean that you can use that to help get those estimates, but I think once you have the doubling and the the Poincaré.
Oh,
then I think
right. Yeah, Ricci lower bound is like a volume doubling, isn't it? Yeah.
Basically, it goes like you can do modes of iteration as long as you have those two things. So
Okay.
it's the brief proof.
Yeah, I don't know, but
Yeah.
okay, yeah, cool. But yeah, non-negative Ricci is a nice little condition just to assume.